Hello, good morning. I, SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, video 147. It is for BSc Part 1, Organic Chemistry, Paper 2, Unit 1, Structure and Bonding. Resonance. When a single structural formula of a compound could not explain with its all the physical and chemical properties, then two or more hypothetical structures have been suggested. For example, benzene, Kekulé structure, Dewar structure, and resonance hybrid. See here, this is the acetate molecule. This resonance hybrid may be defined as the actual structure of all different possible structures that can be written for molecule without changing the relative position of its atom. Rules for resonance. The various resonance structures should differ only in the position of the electrons and not in the position of nuclei. See here, diazomethane resonating structures. In contrast, structure 3 and 4 are not resonance structures because they differ not only in the position of electrons but in the position of atoms as well. 3 and 4. All the atoms taking part in resonance structures must lie in the same plane. All the canonical structures should have same or nearly the same amount of energy and stability. Kekulé structure, alloy cation resonating structure. Resonance structures having light changes on adjacent atoms are of high energy and hence contribute little towards the resonance hybrid. Highly stable makes large contribution. Highly unstable makes little contribution. Properties of resonance hybrid. Stability. Stability of the molecule is due to delocalization of electrons and is measured in terms of resonance energy. In other words, larger the resonance energy, more stable is the compound. For example, benzene, its resonance energy is 36 kilocalorie per mole. 1,3-butadiene, its resonance energy is 2.99 kilocalorie per mole. Here, this is due to the reason that pi electrons being less tightly held by the carbon atoms repel the bond pair of carbon-hydrogen bonds more than bond pairs of the carbon-hydrogen bond repel each other. Bond energy, whenever covalent bond is formed, some amount of energy is always released. Conversely, the same amount of energy will require to break the bond. The amount of energy required to break the 1 mole of hydrogen molecule into individual atom is 104 kilocalorie per mole. Hydrogen free radical. There are two kinds of bond energy: bond dissociation energy and bond energy. Bond dissociation energy. Here, methane molecule is there. Dissociation energy for methane, methyl hydrogen, it is 102. Methyl radical to hydrogen, it is 105. Methyl to carbon hydrogen to hydrogen, it is D3 108. CH is 83. So total bond energy D1, D2, D3, D4 divided by 4, it is 99.5 kilocalorie per mole. It is bond energy. As a result, benzene is much more stable and is not easily oxidized by KMnO4 even under drastic conditions. Whereas 1,3-butadiene is much less stable and is thus easily oxidized by KMnO4 even under mild conditions. Bond length. See here, due to the resonance structure, their bond length is also affected. Here, carbon-carbon bond length, it should be 1.54, but in benzene, neither it is a single bond length nor it is a double bond length, but it is average about 1.39 angstrom. In 1,3-butadiene, carbon-carbon, single bond, carbon-carbon, double bond. Their bond length 1.35, here it is carbon-carbon single bond length is less 1.48 and double bond length is slightly higher, it is 1.35. Difference between tautomerism and resonance. Resonance, different resonating structures differ only in the position of electrons but not in the position of atoms. Whereas tautomers differ both in the position of electrons as well as the atom. For example, benzene, resonance in benzene. Due to delocalization of pi electrons, propanone or acetone, propane 1 in 2 all, they are tautomers. So here, delocalization of electron as well as atom. In resonance, the various resonance contributing structures are not be isolated by isolation is not possible or isolation is not possible. Tautomers actually exist and can be isolated in suitable condition. The resonance structure are not in dynamic equilibrium, so shows by double-headed double bond arrows. The tautomers are in dynamic equilibrium, so shows by this type of double arrow, opposite arrow. Resonance leads to stabilization of the molecule. It does not lead to stabilization of the molecule. For example, benzene, it is having resonance energy 36. It is more stable than compared to 1,3-butadiene. Its resonance energy is 3 kilocalorie per mole. So we can calculate here resonance energy of benzene. So difference between the theoretical and experimental value, it is about 36 kilocalorie per mole, which is also we had discussed in earlier lecture. So thank you very much for today's lecture.